Exercise number 26 is a question about analytic geometry. We are asked to find the point on the curve y equals the square root of x that is closest to the point 3, 0. So just to get a rough sense of what this looks like, we're in the xy plane. And if we consider 1, 2, 3, 4, so we'd have 4, 2, 1, 1, 0, 0, and you're going to have a parabola coming through here. The point 3, 0 is located right here. That's at 3. And we're trying to find the point on the curve y equals the square root of x that is closest to this point. Okay. Now, if you look at this point here and you were to just go straight up, that's reasonably close. That would be at 3 square root of 3. But there's kind of a slant to the problem, right? You would expect actually, if you kind of look at the kind of slant going on here, that if you could kind of go this way, maybe get something closer to a right angle, roughly, maybe, that would probably be a little bit closer. So it looks like the closest point on the curve might actually have an x value a little smaller than 3, right? Could be a little bit to the left of that. It's nice to do this up front so that we know about what to expect, so that if we get an x value that's too small or too big, we can tell pretty quickly that something seems to have gone wrong. Or give it a closer look and figure out why our estimate was wrong. Maybe our analysis turns up something we weren't expecting. So we want to come up with a function to describe what we're trying to minimize. We're trying to minimize the distance, right? We have the point 3, 0, and we have some arbitrary point xy. These xy points describe every point on the curve here. And we want to minimize that distance. And you probably remember the distance formula. Hopefully you remember the distance formula. But that's kind of a pain to mess with, right? So let's think about this. We have the point 3, 0 and the point xy. And if you just go straight into the distance formula, and I don't recommend doing this, if you go straight into the distance formula, you get something like, how do I want to do this? I guess we'll write this as x minus 3 squared plus we have y minus 0 squared. Now we can use the fact that y, well, we'll get to that in a minute. We can simplify this a little bit, but you can see that this is going to be a little bit unpleasant when it comes time to take a derivative, right? There's a trick that we often use with optimization problems, which is that distance is always non-negative. And if you have a non-negative value, if you have two non-negative values, and you square them, so you run them through the x squared function, the outputs, the distances will change generally, but the larger value will have a larger square, because for non-negative inputs, the squaring function is strictly increasing. So if you have a larger distance, then if you have two distances and one of them is larger, and you square both those distances, the larger distance has a larger square. So what we often do, actually, instead of optimizing distance, we try to optimize the squared distance. Right? So we don't have that radical. And a lot of our algebra is easier, a lot of our calculus is easier. We also remember that we're only concerned with xy points that are on this curve. So y is equal to the square root of x, which means that when we square y, x minus 3 squared, y squared is just equal to x. So we have this nice, simple expression, and that can be our optimization function f of x. We define a function f to be the squared distance between those 2 points. And let's go ahead and expand this, clean this up a little bit. We have x squared. That'll be a minus 6x plus x, looks like minus 5x, and then plus 9. So for any x value, this represents the square of the distance between the corresponding point on the curve and the point 0, 3, or 3, 0, rather. Let's check to make sure that this makes sense, perhaps. Suppose x equals 0. If x equals 0, we should be at the origin, and we should end up 3 units away. And if we plug in 0 here, we get 9, which again is the squared distance. So that's right. And 3 squared gives us 9, so that works out. Now we're trying to minimize the distance. So let's take the derivative to look for critical points. We have 2x minus 5. This is always defined, so the only other place critical points could appear is when this equals 0. Add 5, divide by 2, we get x equals 5 halves. If we use a first derivative test on 5 halves, we see that for lesser values of x, this is going to be negative. For greater values of x, it'll be positive. So the function is decreasing and then increasing, so it looks like we've found a minimum. If we use the second derivative test, f double prime is equal to 2, which is always positive, so that means that this is concave up, and again we have a minimum. So the we expect the minimum distance at the point when x is equal to 5 halves, and y, remember y is equal to the square root of x, so we have the square root of 5 halves. And that is the point at which we have the minimum distance, which I believe is what they were asking for, right? Find the point on the curve that is closest to the point 3, 0. So 5 halves, that's 2.5. That's right here. So we do indeed get a point pretty close to what I was talking about, a little to the left of 3. As with any problem, always make sure that you go back and reread what exactly they're asking for. In this case, we were looking for the point on the curve, so our answer is the point. In my previous video example, we're not looking, they didn't ask us for the x value to cut off, they asked us for the maximum volume, so we had to compute the volume. Here they didn't ask us for the distance, so we don't need to actually compute the distance. You could stick that in there and figure out what the distance is. But they didn't ask us for it, so there's not much point in doing so unless you're curious. But again, in many ways, this is much like any of the other optimization problems. You have some things that constrain what you're looking for. You have, we come up with an optimization function that depends on x and y in this case. We don't want 2 variables, but we know what y is in terms of x, so we can replace that and reduce it to a function just in terms of x. The biggest trick, like I say, is it's often easier to use the squared distance. You don't have to. You could just, take d, the distance, as the square root of such and such, and you would then have the square root of x squared minus 5x plus 9, and then you could take the derivative of that, but that's more of a pain, and then you have to analyze the results, and that just kind of wastes time. So here's a little handy trick for dealing with those sorts of distance problems.